Okay, good morning, everyone. Okay, so thank you for coming in today. Okay, so for today's lecture, what we'll be doing is we'll be covering the topic on memory. All right, and this will and there's only one more lecture left for next week, and the last topic is on virtual memory. All right. Some of you have been asking about the tutorial for this week. All right, so this week some of you are affected because your tutorials are on Thursday and Friday. Okay, so your tutors might have already contacted you, so they will do two things. Either they may release a recorded video, okay, to explain the solutions, or they may discuss the tutorial 7 next week. All right, so for next week's topic on virtual memory, there are also some tutorial questions. Okay, what I will be doing is those tutorial questions for next week I will go through in the lecture slot itself. All right, that means once we finish up the lecture, okay, I will release the solutions, everything earlier, so you can also have a look. So once we are done with the lecture, I'll also discuss the tutorial questions during the lecture slot itself. All right, so the only new topic next week is the virtual memory, so there'll be just one or two questions on that. All right, and then we'll discuss on the memory that we are going to cover today. Okay, so let me get started. Okay, so towards the end, I'll talk a bit about the project, okay, and things you need to get ready for. Yeah, so today's topic is fairly, I think, manageable. Okay, so there is, like I said, there's no more structured lab activities. So you just have to focus on putting this together for your project, okay, and getting it ready. Okay. In terms of today's lecture, I think we should be able to do it in slightly over an hour. Okay, so most likely I will just go through the whole topic and then we can end early. All right, instead of having a break and so on. All right, so let's get started. Okay, so this concept of memory, okay, we're going to be discussing the different components of the process memory, okay, and how it sorts of the OS sort of manages it. All right, to make sure that every process or every task has the enough memory, okay, to run and fulfill the requirements. Okay, and this memory is of course a very important topic or important concept to understand, especially in the embedded domain. All right, when you are developing a PC program, all right, you generally don't think of memory constraints so much, right? Because you always can always upgrade your PC or add on more memory and things like that. So memory is not really a concern in most PC applications. Whereas in an embedded system, okay, you are very much constrained by the amount of memory you have. Okay, so even adding a new array, a new loop, okay, some additional lines of code can suddenly make you just exceed the limit. Okay, and then that's it, you can't download the code anymore. All right, so you have to be very mindful of how much memory you have. Okay, that sort of directly impacts how big your code size is, how effectively you need to declare your variables to use them or reuse them, okay, instead of taking up too much of space. Okay, so let's look at different segments of memory. All right, so the first thing is code. All right, so when you write your code, okay, when you compile it, that is basically your executable code, which you also call the binary, okay, of your program, okay, together with all the libraries that is compiled together with it. All right, and this is known in advance, right? Because the moment you click on compile or you send a compile command, it automatically knows how much space it needs for the code. All right, so that is basically what we call the text segment of your of the memory space. Okay, so that is where the code gets allocated to. Okay, the next is some variables. Okay, so variables that exist, okay, could be different types. So you have global variables and static variables. Okay, so for global variables and static local variables, there are two areas where they can be allocated. One is data, the other is PSS. All right, so if I declare a variable, okay, and I initialize it, okay, with a value, okay, then that goes into the data segment. If I declare a variable but I do not initialize it, okay, to any value, okay, in the code, then it goes into the BSS segment. All right, and generally by default, most compilers, what they do is data in the BSS segment is initialized to 0. All right, again, this is usually a compiler or a linker setting. Okay, so by default, most of them will initialize this BSS content to 0. Okay, then there is of course dynamic memory. So dynamic memory is while you're running the program, you allocate the memory that you need. Okay, and that is done using two main functions, malloc and free. Okay, and the thing about this is OS does not know in advance, correct? Because only when your program is running, you may do a sort of runtime decision, okay, or how much memory you need, and then you try to allocate that memory space. Okay, so that because it is unknown in advance, so you need to allow some room to grow. So that is where the heap comes in. So as you can see, the heap has a sort of a pointer base where it sort of grows. Okay, so the size of the heap will grow, okay, as and when you need more space. Okay, and the other area that where you also need some growing space is the stack. Okay, so this stack is used for a few things. Firstly, your function parameters, and at the same time your local variables. Okay, so whenever you create a function, create a variable within a function, so we call it a automatic variable or a local variable. So that is within the stack space of that particular task. All right, and at the same time, all right, I'm sure you have learned some assembly language programming, so you know that the stack is also used whenever you jump into a function. All right, so whenever I need to jump to a function, okay, I use it for function parameters as well as the return address. All right, so if I say this is my main program, okay, and I call function A. All right, so when I call function A, maybe I pass in 3 variables. Okay, so these 3 variables must go onto the stack. Okay, because I'm passing in, right? But again, this may differ, okay, for different processes. All right, I'll talk about that in a while. At the same time, once you finish function A, okay, that means I need to jump to function A. Okay, and when I finish function A, I need to be able to come back to where I left off. So this address here, this address must also go onto the stack. Okay, so these are some of the sort of concepts you probably have studied when you were doing some assembly language coding in other modules. All right, so that is where the stack is used. All right, and generally stack has 2 main functions. We call it the push and the pop. All right, so those are of course at assembly level. Okay, and all this is automatically taken care of by the processor itself. Okay, when you're jumping to a function and so on. Okay, so when you compile the code, okay, all of this is sort of automatically taken care of for us. All right, so this sort of gives us the overview, all right, of how the layout is in memory. Okay, so you have the text segment, your data, your BSS, your heap, as well as your stack. All right, so again, this is another example on the stack. All right, so as you can see, when I first run my main program, okay, I create 3 local variables, A, B, and C. Okay, and since these are local variables, they will occupy the stack space, okay, that is allocated to the main task. Okay, when I call function F, okay, I am passing in A and B, okay, and A and B get mapped to X and Y. So I need to create some space for X and Y. At the same time, within function F, I also create another local variable. So that is also that. All right. So of course, what is not shown here is the return address and so on. Okay. So I'm just showing you the variable that are created in terms of the return address that is also pushed onto the stack. Okay. So just now I mentioned that this pushing of variables onto the stack may differ, okay, for different processes. All right, and specifically for ARM, okay, since we are dealing with ARM, okay, for ARM, it behaves in a slightly different way, okay, for efficiency. All right, so what they do is they follow this sort of protocol called AAP PC, the ARM procedure call. All right, I can't remember what the first A stands for. Okay, but it's basically an ARM procedure call, sort of sort of a framework. Okay, and what they do is they set aside the first 4 registers R0. So if you look at the ARM register space, you have a lot of registers. Okay, so R0 to R3. Okay, the first 4 registers is set aside for variables. Okay, whenever you do a function call, that means if I create a function f and I only have 2 variables to pass in x and y, they will occupy 2 registers. Okay, and over in function f, I will get the values through the registers. Okay, so up to 4 parameters I can pass through the registers. Okay, only if I exceed 4 parameters, then I use my stack. Okay, again, this is for efficiency because, as you know, memory access is always slower than register access. Okay, registers are always the fastest sort of space you can access within the processor. All right, so if I keep everything within the register space, I can do things very quickly. All right, so that is why they do this. All right, but only up to 4 parameters. Okay, beyond 4 parameters, then you still have to use the stack for the additional ones. All right, so that is how ARM works. So again, when you deal with different processors, okay, they may have their own register definitions and they may utilize them differently, all right, to optimize the use of the internal registers during such situations. Okay, so in the memory layout example, let's look at this code over here. Okay, so as you can see, we have some global variables. Okay, we have a function. Within the function also, you have some variables and some code and so on. Okay, so let's see how the allocation is done. And so firstly, of course, your text. Okay, your entire code will occupy the text space. All right, and that is, again, like we said, it is known beforehand the moment you compile your code. Then you have 2 components in your data. Okay, one is your global variable, which is this. Okay, and it is declared with a value, so it goes into your data space. And the other is your static variable. Okay, so static variables, you know that they retain their value, okay, even after you exit the function. All right, so in order for you to retain the value, you cannot put it on the stack. All right, so once you anything on the stack, once you exit the function, you lose access to it. Right, so that is why when you declare a variable as static, it has to be placed somewhere else, and that is the data segment. Okay, then you have another global variable here. Okay, but this is not declared with any initial value, so it goes into the BSS segment. Okay, and then you have malloc. Okay, so malloc is again a runtime allocation. So based on the value of string length, I would allocate a particular size. All right, and that is in the heap, okay, of the memory space. Okay, and then finally you have a local variable here. Yeah, a pointer variable. So that local variable is within the stack space of your memory. Okay, so as you can see, in just one simple code segment here, you are already utilizing all the different sections of your memory layout. Okay, and of course, memory allocation and deallocation happens in different locations or times. All right, so anything that is known upfront, all right, a program startup, okay, you already can allocate it. All right, so for example, global and static variables are allocated the moment you start up. Okay, local variables like inside a function is on the stack. All right, so only when you call a function, you allocate the memory for it. Okay, and for dynamic memory, when you call the malloc function or the free function, then you get the allocation or deallocation. All right, and of course, deallocation comes, okay, when you finish the program, okay, for global and static variables. Okay, for local variables, okay, whenever you return from the function, okay, that means once you return, that stack space that was allocated to you is freed up, so you are able to clear those local variables. And finally, for dynamic memory, when you call the free function, you free up the memory. Okay, so this is just giving you a simple example. So let's just assume that this is my heap. Okay, and P1 okay, is initially allocated to 3 blocks, okay, based on this malloc function over here. So once I allocate 3 blocks, okay, so when I execute this first line of code, I'm telling the program that I want to allocate, okay, 3 blocks of code over here. Okay, now once I allocate, all right, then I will call another malloc. Okay, so as you can see over here, what I'm showing you is one sort of allocation mechanism where automatically I look at the next available space. Okay, so once P1 has been allocated a certain memory region, okay, I know that my next free space is starting from here. Okay, so later we'll look at some other policies. Okay, so this is one policy where you straight away start from where you left off. All right. So P2 continues, okay, and then P3, okay, another block. Okay, so when I call free P2, that means I am telling the system that I want to free up this memory, okay, that was originally allocated to P2. Okay, then again I can have another allocation, and then I can free up P3. All right, then when I have another allocation of P5, so in this example, what you're doing is you can see that P5 went back to the same slot that was originally freed up, okay, from P2 and P3. Okay, so originally P2 had a size of 1, okay, then now P5 is asking for a size of 2 blocks, correct? But the total size here is 1 plus 4, so total I have 5 blocks over here, and I need 2 blocks, so I go back to where P2 started and I allocate these 2 blocks. Okay, so again, there are different policies, okay, on how the memory can be allocated whenever a process asks for it. All right, so we will look at that in a while. Okay, then in the end, when I'm done with everything, of course, I can free up the memory. Okay, so of course, in a when everything goes well, it is good, all right. But at the same time, all right, you can also sort of have some wrong usage of allocation of memory, all right, and that can lead to a lot of issues. Okay, so one of this is this thing called leaking memory. All right, so if you look at this example, okay, what is happening? So inside the main function, I call f. Okay, and inside f, what am I doing? I am allocating, okay, or I request to allocate 8 bytes. Okay, 8 multiplied by size of jar, so this is 1 byte. So every time I call function f, I allocate 8 bytes. All right, and then I use it, and then I just return. Okay, but what happens? I did not call free. Okay, I'm supposed to call free, but I did not call it. Okay, and this is an issue, a very big issue. Okay, you might think that it's only 8 bytes, right? Correct? It's not much of a big deal. Okay, but you have to imagine that if I only happen to call f 1 time and it's only 8 bytes, then okay, maybe you really don't see it as an issue. Okay, but if let's say this f was inside a loop, okay, was inside a loop, okay, where maybe periodically I keep calling it, then what happens? Then every time I call f, I allocate 8 bytes. I allocate 8 bytes, but I never free it. Okay, and this kind of software bugs are the most difficult to catch. Okay, why? Because you will not see a problem when you boot up. You will not see a problem when you run for 1 hour or 2 hours. Okay, but maybe after 1 day or 2 days, suddenly the whole system crash and it reboots. Correct? And then you run again after 2-3 days, again the whole system crash. Okay, so it is a very difficult thing to debug because you, when it's running properly, you think that everything is going well. Okay, but then you didn't realize that you were actually allocating a small amount of memory every single time. Okay, and over time you keep eating into the amount of space you have, and then eventually you run out of space. All right, and then the whole system just crashes. Okay, so that is why some of these memory related sort of issues are very tricky. Okay, because they do not cause an immediate issue that is visible. Okay, they only sort of have a side effect much later on. All right, so that is where the challenge comes in. All right, so this is another example. all right, where you have dangling pointers. Okay, so dangling pointer means, so when you have a pointer, you know that you are using it to point to some memory, correct? So you need to first assign it to the address that you want to point it to. Okay, so if you look at this example, what is happening? I call function f, okay, and inside function f, what do I do? Okay, I create an array, and at the end of the function, I return p. And what is p? Okay, so an array, okay, if you look at the name of the array, this is actually pointing to the address of the first element. All right, p is actually another short form for the address of the first element in the array. So I'm trying to return the address of the first element in this array, okay, and try to access this array from the main function. So I have another pointer here. So I want this result pointer here to point to this address to access it. Okay, but what is the problem? The problem is this is a local variable. That means it goes on the stack, which means that the moment I exit the function f, I am already clearing that stack. Okay, so technically when you say clearing, it's not say you clear it by resetting it to 0 or not. No, the content is still there. It's just that it can be overwritten anytime the moment the next stack usage comes along. Correct? So it means that I cannot guarantee that subsequently, okay, initially, yes, initially when I return, I can say I am pointing that. But very soon after that, I may lose that information because somebody else may take that stack space, okay, to do something else. All right, so you think that you are accessing this data, but actually you're not. You are now accessing some other data because the stack is now utilized for other things. Okay, again, these are things that you will not detect because it does not show up as a compiler error or a warning or anything like that. Okay, maybe it might show as a warning, okay, depending on how smart the compiler is. All right, okay, in some cases they may be able to flag off some of these things, all right, that you're trying to point to unallocated space or something like that. Okay, so some compilers, okay, may be smart enough, they may be able to warn you, but in some cases you may not get any warning as well. All right, so you may run the program thinking that everything is correct, but again, it is not exactly because you are pointing and you are still doing something. Okay, so subsequently, again, if you use the pointer, it will still work because it's pointing to a place in stack. All right, but the thing is, you are now going to mess up the data that is now actually being used by some other function. All right, and then you have some other downstream problems later on. Okay. So in terms of so that were just like two examples, okay, of how not carefully considering the usage of pointers and memory allocation and so on can lead to a lot of tricky bugs to deal with. Okay, so now let's look at memory allocation. So in memory allocation, whenever you request, okay, the objective of the OS is supposed to allocate the memory that you requested for, all right, and as and when you free up, it's supposed to let the system know that this memory is now free. Okay, so many processes or many tasks may request, okay, periodically or ad hoc basis, okay, for memory, okay, and you must be able to address it. Okay, so when you say memory allocation, okay, so this is an example of a simple memory allocation where I have a character pointer and I say I malloc 4096. Okay, so when you do this, what is happening? That means I'm saying that I want 4096 bytes of data to be set aside, okay, when I call this malloc. Okay, and the address of this, so this address here, the starting address is 8192, okay, as an example. So that address is now allocated to the pointer variable. Okay, so you can think of it again simply like an array, right? Because you can imagine that now I declare an array of 4096 bytes. And now pointer, okay, this variable pointer PTR is pointing to the first element. All right, so a pointer and array, of course, are sort of interchangeable in C. All right, you can use pointer index, or you can use array index, okay, and both will work, okay, interchangeably. So whenever you say memory allocation, that is what you're doing. You're trying to allocate memory, and you want to get a handle to the memory, right? And that handle is the return address. So the return address has to be captured by a pointer variable. Okay, so that is what we are doing here. Okay, so of course, memory allocation and deallocation can cause another issue, which is also called, which we know as fragmentation. All right, so in fragmentation, basically what happens is, because this allocation and free is continuously happening while your program is running, all right, you can sort of have pockets of memory space here and there, where some is used, some is not used, and so on. All right, and that of course causes some issues. All right, so external fragmentation, okay, is caused when you have variable allocation sizes, whereas internal fragmentation is when you have fixed allocation size. Okay, so what are these two types of fragmentation? So if I look at this example here, for external fragmentation, what is happening is, for the first 4 lines of code here, I'm going to allocate 400 bytes of memory. All right, so when I free the second block, okay, and when I free the fourth block, okay, I free up 2 blocks, okay, but subsequently when I try to allocate 200 blocks, okay, of memory, or 200 bytes of memory, okay, it is not possible, because okay, there is no contiguous block of 200 bytes available. Okay, even though the total space is more than 200, all right, but I only have 100 and 150, okay, as 2 separate blocks. Okay, so when I try to malloc 200, it will be not possible. Okay, so that is where the fragmentation issue is visible. Okay, for internal fragmentation, how that happens is when I have a fixed allocation size. So regardless of how much data I need, I always allocate in blocks, okay, of a particular size. So in this case, the example is 100 bytes. So if I want 90 bytes, I will still allocate 100, then I will use 90, but the other 10 is not used. Okay, similarly, if I want 120, I need to allocate 200, okay, but 80 is not used. Okay, and then if I allocate another 10, okay, I only use 10, but 90 is free. All right, so as you can see, I have a lot of internal fragmentation because I allocate in blocks, all right, but only part of the block is used. So when I want to do the last one, okay, malloc 50, it doesn't work, correct, because all the blocks are already used up. Okay, the amount of space I have 0 to 400 is already used up, okay, because of the internal fragmentation. All right, so we will look into how to compact the fragmented memory later, okay, for external fragmentation. For internal sort of fragmentation, okay, one of the things we need to be mindful of is also we need to keep track of where is the space available. Okay, if you want to access the next available block and so on. All right, so we will look at that as well. Okay, how to keep track of where is the next block and how much space is available and so on. Okay, so if I look at this example here, what you have some allocation of space, all right, where you have whole pointers here, all right, to keep track of the next available hole and the previous hole. All right, so if you see here, okay, this next pointer will point to the next available hole that I have in the system. All right, so I need this for external fragmentation. Why? Because in external fragmentation, you try to keep track of holes so that the next allocation request that comes in, you sort of are able to know where is the hole located. So I need to sort of keep track of this information. For internal fragmentation, you just need to know which blocks have been utilized, because within each internal block, you already allocate the memory, and the free part you can't touch it. Alright, whereas for external fragmentation, you have a mix of holes and chunks. That means holes are the available space, chunks are the used space. Alright, so I need to sort of keep track of where is the memory that is available, okay, using a sort of a list or a pointer. So in this case, the next pointer always points to the next available space, and the previous pointer points to the previous available space. Okay, so I can sort of go back and forth, okay, to find the hole that is most suitable for me to use whenever a request comes in. Okay, so in a free list, okay, what you can do is you can look at how to allocate the holes. All right, now which section of memory is used depends on the policy. Okay, so the policy part will come to that a bit later. Okay, but generally, if your holes are large, all right, that means if I have a huge chunk of memory available, I can always satisfy the request that comes in as long as they are within the space. All right, so it's always better to have more space and I have small requests of memory. Okay, whereas you have very little space and you have a large request and you can't do it. All right, so that is where the keeping track and the list comes in. Okay, when memory is freed, all right, you put it into a free list. Okay, where you say that the memory has been freed up. All right, and once it is freed up, what I can do is I can actually do a merging. Okay, if possible, with any hole before or after that. Okay, so for example, if these two chunks of memory are used up and I free up the one in the middle, then I can then it's still if you don't do any compacting, okay, which we'll cover later on, you still keep it as it is. All right, okay, but later on, of course, we will talk about compacting memory, where I can choose to move this chunk here so that all the used chunks are together and all the holes are together. Okay, but that is compacting. All right, but if let's say I don't do compacting, I can just say I do not want to merge and I keep it as it is. All right, but if I have a free space, all right, and a hole is there on one side of it, I can choose to merge. All right, then I can create a bigger hole. Okay, same thing over here or here. So the merging is more easier, okay, the moment you have holes next to each other. Okay, that means some space is freed up next to or before each other. Okay, so now we're looking at this example of the deallocation of memory. Okay, so now currently this chunk of memory is used up. Okay, and now I want to free it. Okay, so once I free it, okay, as you can see, there is already a hole over here, so I can do a merge. So since I'm able to do a merge, I can now free up both of these pointers. Okay, so the previous pointer can be removed from this hole and the next pointer is also removed from this hole. Okay, so now I have a bigger hole, okay, by the combination of the chunk and the earlier hole. All right, so these are the sort of policies that I mentioned just now. Okay, how do you go about finding the sort of space that you want? All right, so in this example, okay, the first algorithm we will look at is what you call the best fit. Okay, so these policies, okay, on how to allocate is usually controlled within the OS. Right? So the OS will have some policy that it will implement by default, okay, or how it will allocate as and when these malloc requests come in. All right. So if the policy is best fit, then what it will do is it has to search the entire list, all right, and try to look for the most closest hole, that means the smallest hole that is able to satisfy the request. Okay, so if my request is 150 bytes, okay, then since I have 3 blocks here, I'll choose the one that is closest to it, which is 200. All right. Okay, so of course, the issue with that is you tend to leave a lot of small holes, right? So imagine the ones I allocate 150, then I still have a slot of 50. Okay, and if nobody requests for 50, then that small hole would be there. all right, unused. Okay, the other one is worst fit. All right, so in the worst fit, you try to pick the largest hole. All right, and this is one of the preferred options. Okay, why? Because if I pick the largest hole, all right, and I try to work on it from there, then I still have a lot of space available, all right, to keep on utilizing it until it reaches a very small amount of space left. All right, so even if I allocate 150 over here, I still have a huge chunk still available. Okay, but it doesn't mean there is no fragmentation. Right? Eventually, there will still be fragmentation. All right, because eventually they'll come to a point where I use up until again there's still very little left, and again I may not use it, and there's fragmentation. All right, the next one is next fit. So the next fit and the first fit are two sort of related. In the first fit, what you do is you start from the beginning of the list, and the moment you come across the first hole that is big enough, you straight away use it. Okay, so you always start from the beginning and then you come. So if let's say now 150, I would allocate 150 here. Okay, so eventually I'll have 850 here. Okay, so I would have used 150, 850 left, and my pointer would, the next time that I traverse through, I'll come to this location here. Okay, the 150. So this marker over here. Okay, so the next fit, okay, is similar, okay, except that in the next fit, I will always continue from where I left off. Okay, so for the first fit, I'll always go back to the beginning. That means I come back to here. This is my starting point. Okay, and then I traverse through the whole memory to find the hole that is large enough to fulfill the request. All right, and once I fulfill, then I go back to the beginning again for the next allocation. Whereas in the next fit, okay, once I finish, okay, if my pointer is here, the next allocation will come from this. Okay, so if my next allocation is, let's say 1000, okay, then of course this is not big enough, and then I'll come here. Then I'll come here and then I'll allocate 1000. And then my pointer will come here. All right, so if after I do 150 and then I do 1000, okay, so let's say my next allocation is 100. Okay, so my next allocation is 100 means I will carry on from here and allocate another 100 for next fit. Whereas if I go to first fit, I'll come back here and allocate the 100 over here. Okay, so it's just a matter of where I carry on from. Okay, in the first fit, I always go back to the beginning and start from the first hole that I come across. In next fit, I just continue from where I left off. Okay, so again, all of them have their own sort of pros and cons, but in the end of the day, there is still fragmentation. Okay, regardless of whichever policy you choose. Okay, because they'll always come to a point where there may be small holes here and there that are still separated from each other, and there's no allocation to that. All right, so that is where the compaction comes in. All right, so in compaction, basically what we need to do is you can you can sort of combine them together. All right, the holes to create one big hole and one big chunk. All right, to deal with internal fragmentation, you can use what you call paging or segmentation. So this one we will cover in next week's lecture on virtual memory. All right, so for compaction, okay, just give me a minute. I don't know why is this continuing here. Okay. Okay, so for compaction, basically what we are trying to do is we again look at the holes that are available, okay, and we try to push all the holes to one end of the memory space and push all the chunks to another end of the memory space. Okay, of course, when I draw like that, it seems like so easy, right? But actually, it is quite a challenge, right? Because you need to keep track of all the pointers, correct, of all the chunks and all the holes, and then you need to physically copy that data around. Right, so I need to copy this whole chunk of data from one address range over to another address range. Okay, so it does involve quite a lot of work, right? And usually when you want to move huge chunks of memory around, okay, within the processor, okay, there is one peripheral, okay, your KL25Z also has it, which is what we call DMA. Okay, does anybody know what is DMA? I think you all should know, correct? Yeah, direct memory access. Okay, so in DMA, basically what happens is, okay, you allow the processor, okay, or the DMA itself is a hardware block, all right, within the processor that can do data transfer for you, okay, in the background, okay, while you are doing other things as well. Okay, so you can sort of run it in parallel while you are doing your other main stuff. All right, but again, all this requires some additional effort in the configuration, in setting up and keeping track of all these pointers and all. All right, but that is one way of doing a sort of defragmenting or causing or sort of clearing the fragmentation issue. All right, so of course, like what I said, it is actually a huge overhead, all right, to do. Okay, and of course, I think most of your laptops also, if you go to your Windows settings and so on, under memory, there is also a disk defragmenter that you can see, where you actually can see how much your hard disk is fragmented, okay, and you can run a defragmentation process as well. All right, of course, in a PC setting and so on, again, you don't worry so much about, I mean, you have more computing power and you have a lot more actual battery life and power, so you don't think of that as an issue. But in an embedded system, that overhead involved in trying to do all of this can have a huge impact on the power consumption of the device, okay, which you need to factor in as well. All right, so one other way of handling it, again, instead of trying to do all this compaction and so on, all right, is trying to keep what we call multiple free lists. All right, that means your memory itself, you break it up into a list, okay, multiple lists, where each list has pointers to different pre-allocated sizes of memory. All right, so in this case, okay, for 128 byte blocks, I have certain blocks. For 64 bytes, I have certain blocks and so on. All right, so I already pre-allocate the sizes. All right, and the moment a request comes in, I quickly go and see which list closely matches that request, and I allocate from that list. All right, so that is one way of keeping all this a lot more easier to manage. Okay, so in this example, all right, what you can do is, if I have a 16 megabyte of memory, I can split it, okay, into 8 megabyte, and then the other 8 megabyte I split it, and so on. Okay, so I can of course keep on dividing by 2 and splitting until a point of time where I get the desired size that I want. So in this case, okay, for example, if I want a 3 megabyte space, okay, what I do is I can continue to split, okay, along one branch until I get the size that is able to fulfill the request, okay, which is the closest matching, and then I can stop. So I don't need to split all the way first, but I can split as and when the request comes in. Okay, so for example, in this case, this 3 megabyte could be allocated, okay, to one block over here, and subsequently I can use the next block to free up to allocate or to divide even further if I have another smaller request and so on. Okay, so that is one example of how you can use free list. Okay, so for example here, I have 1 megabyte of memory. Okay, and I only want 100K. Okay, so what can I do? Okay, so instead of the earlier where I just say first fit, best fit, and so on, I can start to divide it up, okay, into multiple sort of subdivisions until I get one that is closest enough to match my request, and then I allocate the whole. All right, so now I have a sort of multiple free lists of different memory chunks, okay, depending on what I need. All right, then extension of this is what we call the buddy system, where what you have is each hole in a free list has a buddy, where you can use that buddy to combine and create a bigger hole. Okay, but again, this only happens if there is alignment on the higher level boundary. Okay, higher level means if I want to do any sort of grouping here, I need to check whether it's aligned to the higher level boundary. So in this case, this 2K and this 2K are aligned to this two boundary above. Okay. Similarly, this 2K and this 2K are aligned to this boundary and this boundary. So I can group them. Whereas these two in the middle have a cut in between at the higher level boundary, so I can't combine them. All right. So this is one way of easily managing the allocation and freeing. Okay. So let's look at an example here. So in this case, I have 1 megabyte. Okay, the same thing. Okay, and I want to allocate 100K. So what I do is I split up. So first 512, 512, I split up. Then I split up again, and then finally I allocate 100K. Okay. Now I want another 64K. So this 64K, where can I get it? I can split up the 128K into another 264K and allocate it. And if I want another 240K, I can allocate it from the other list, which is the other end of the 256K. Okay, and I want another 256K. Then I split up again. Okay, so as you can see, the memory does not split up in advance on all the layers. All right, it only splits up as and when the request comes in. All right, and once I free up any memory, all right, if possible to merge, I will merge. All right, but I can only merge if the size is aligned. All right, that means the current size and the other size is the same and is aligned to a higher level boundary. Okay, so as you can see, when I free up the 240K, okay, I free up this entire 256K. Okay, but I can't do any merge with the 64K because it is not the same size. All right, when I free up this other 256K, which is this one, okay, then both of them are aligned to the higher level boundary, okay, which is the 512K. So I can do a merge. All right, and then finally, of course, if I free up the rest, I can merge again, and then subsequently the whole process will repeat. Okay, as and when I have allocation, I can split up, and then when I free up, I can merge again. Okay, so this buddy system and multiple free lists is again a more or an alternative way of managing this allocation. Okay, where you don't have to go through the first feed or next feed and so on. All right. So of course, the fragmentation issues are still there. All right. But again, you don't have a really perfect solution. All right. So you still have to deal with some fragmentation here and there. But again, these are alternatives to how you can manage the memory allocation more efficiently. Okay, so that sort of brings us to the end, all right, of this lecture where we talked about the memory allocation and deallocation, all right, and how the OS manages it, all right, and of course, in the first part, how we can allocate or how the compiler and the linker work together to allocate memory based on our code. Okay, so before we end, just some admin matters. Okay. So as I mentioned, the lab is open, okay, this Friday, okay, 5th November, okay, but you can only come during your own allocated lab slot, okay. As I mentioned, if the Friday, on Friday, the afternoon slot is free, you can ask Uncle Jalil, okay, to confirm. Again, I'm not sure whether he will be around, okay, or he may also leave after lunch. Okay, so if he's around and the lab is free, okay, and you want to do some work, you need to ask him permission first. Okay, again, all this is subject to the numbers that are there. All right, because we have to make sure that okay, only the limited number of students are there. Okay, and due to the safe management, Okay, we can't allow you to mingle and all this stuff. All right, so just check back with Uncle Jalil. What are the free slots or free times available if you need to do anything? Okay, so again, this Friday attendance is optional. All right, for the project assessment next week, I will be releasing a more detailed document. Okay, because I think if I announce bits and pieces here and there, some will get it, some will miss it, and so on. All right, so I will prepare everything into a proper document, and I'll put it up and send an announcement so you can read through and be aware of how we're going to manage the entire assessment next week. Okay, yeah, so that's all I have for today. All right.
Prof, yeah, I have a question. So,
yeah.
right, one of the project specification, right, is mentioned that there should be a button in our app which actually establishes Wi-Fi connectivity with the robot. So I was just wondering, how exactly do you code this out? Like, because I understand that the Wi-Fi connectivity is automatically established between the robot and the ESP when the Arduino code is uploaded into the ESP already, right? So how do you like have a separate button to just activate the connectivity again?
Okay, yeah, I think another student also asked that. If I'm not wrong, if you press the reset button, it will automatically reboot and reconnect again. But if you think that is not something you want to do, okay, I will actually be rewording some of these requirements, okay, which may not necessarily be needed. Okay, so I think some of this requirement I will reword it such that as long as the connection is already established, then it's fine.
Oh, I see. Because currently our team is thinking of having some kind of flag in our code, like saying that the value is like 0, right? For not for connected. That means that none of our movements can actually happen for the robot. Then when the button is pressed, then this particular variable's value changes to 1. Then only other movement buttons will operate the movement for the robot. Is that allowed?
Yeah, I think that is also fine.
Okay. Because I was wondering, in the case it's not technically like establishing a Wi-Fi connectivity, you see. So it's just preventing the other.
I mean, yeah, I think in your case, you're just trying to show the status of whether it's connected or not. Correct. So it's also fine.
Oh, I see. Okay, thank you, Prof. And also, right, for the video submission, there's something called the technical overview or something, right, in the video. For that, what exactly do we need to speak about?
You can talk about how you design the hardware and the software aspects of your project. That means maybe you can show some slide about how the whole architecture is, or some clips of how you put the hardware together or things like that.
So it's like which ports are used by the different components in the board, etc. Is it? Okay, got beyond that. And then just my last question, Prof. For the self-driving mode, right? Let's say our team is just using one ultrasound sensor. Is that sufficient, or is it something like we currently place the ultrasound sensor at the front of the robot, so when it detects the obstruction, it automatically turns left and then goes a particular distance and then turns right, without like doing any other form of detection of the distance of the sites. Is that allowed?
Yeah, that is fine.
So it's allowed to hard code the direction in which you will turn.
Yeah, that part is fine. The only thing you cannot hard code is the obstacle detection.
Oh, I see. Okay, thank you, Prof. That's all from me.
When you say it's not detecting the last few threads, what do you mean?
Hi, Prof. Can you hear me?
Yeah, okay.
Right. I was just what I meant is after we create like around 10 plus threads, then some of the like the last few threads inside will not function properly. So previously it was functioning. Then we just added a few more threads, maybe in front of it or something. Then the last few threads, when it's called, it doesn't exist. And you know, in the call stack and memory, it shows all the threads that's running, right? Those threads at the end don't show up.
This new threads, do you declare local variables?
You mean like O thread ID -t like that, or you mean inside the main function you assign it to a variable?
No, inside the thread function itself, did you create like a lot of variables like arrays or things like that?
No, for each of them, it's just changing a pin, so no local variables.
Okay. I'm not aware of any limitation. I mean, so far in all the previous batches, nobody highlighted any issue with creating multiple threads. But of course, I don't know how many threads they created.
Okay. And by the way, the question that you asked just now, whether you have a lot of variables inside, is you're wondering if that thread may be taking up too much space, is it? And then it's not getting activated.
Yeah, because the stack space is very limited.
Right.
Usually, maybe what you can do is if you have other functions that currently have quite a few variables, maybe you move them out to be global variables and see whether that solves the issue.
Okay.
So that's the first thing you can try. Maybe you try to see move your variables out to the global space. The next thing is maybe instead of having more threads, maybe you try to see if some other way you can do it.
Right. Okay.
Yeah, but from what I know so far, nobody has ever brought up this as the issue of limitation in threads.
Interesting. Okay. Yeah, thanks, bro.
Okay. Okay, so if there are no other questions, thank you. I will see you all next week.